Hello, everybody. Good morning, good afternoon. Here in the room at the University of East Anglia and online through our webinar connection. Thank you for joining us today. We are presenting today here a webinar in the series of the European climatic energy mixes work under the Copernicus Climate Change Service Program. Today we are presenting a presentation from Dr. Sue Haupt from NCAR, and it's one presentation. I'll show you in a minute the program. It's about integrating weather and climate information for renewable energy. So I just want to tell you a bit about the European climatic energy mixes first, and we'll for a few minutes, and then we'll go on to the actual talk very shortly. If people cannot hear me or cannot see the slides, please send a message on the chat. Also, you can ask questions at any time using your panel on webinar GoToMeeting. Okay, so I just wanted to tell you a little bit about this European climatic energy mixes activity under the Copernicus Climate Change Service program. As I said, it's a C3S program. And this has developed in collaboration with the energy sector demonstrator to assess how well different energy supply mixes in Europe will meet demand over different time horizons, focusing on the role climate has on the mixes. And you can find more information on the link here. I should also add that the presentation will be provided. And I will ask the speaker. The only reservation is the size, but I think in principle it will be made available. In terms of the activity of the ESM activity under the C3S, this is very schematic. It's the only one I'm going to show you, just to give you an idea what we've done. The activity has now terminated after over 2 years of work, and is now taking this work onto the next phase that C3S will continue under an operational setting. But what we've done here is to take climate variables and calibrate them as best as we can in order for them to be converted into energy variables. As you can see here, then energy variables were assessed in various ways, looking at case studies, effect on interannual variability, and then converted into display images that are displayed onto this graph, which is an interactive demonstrator available online through the link I provided before. So going to the webinar today, which is, as I said, under the banner of this ESM activity, the webinar is focused on the presentation from Dr. Sue Ellen Haupt, and I already gave you the title. I just want to give you briefly a short bio of Sue, and she's a senior scientist and director of the Weather Systems and Assessment Program with the Research Applications Laboratory of the National Center for Atmospheric Research in the US, in Colorado. She also serves as Director of Education of the World Energy Meteorology Council and an adjunct professor of meteorology at the Pennsylvania State University and a counselor of the American Meteorological Society. My name is Alberto Troccoli, as you can see at the bottom here, and I'm chairing this webinar, and also then facilitating the question and answer session at the end. So the talk is going to be about 40-45 minutes with 15 minutes for questions at the end. As I said, the presentation will follow the question and answer. The question and answer will follow the presentation, and you can ask questions at any time using the tab. The webinar is also recorded, and so the recording will be made available online alongside all the other recording from our previous webinars. You can find them on the ESEM website provided at the beginning. And I'll just stop here for now and enjoy the webinar. And now the floor is to you, Sue, if you'd like to come. So, as I said, anytime people on the webinar, let us know if you don't hear well or can't see the slides. We're going to switch now to the other presentation. And you should see the new presentation now. Okay, over to you, Sue. Thank you very much for your time here.
Okay, thank you, Alberto. And I am pleased and honored to be here in Norwich, UK, having an opportunity to talk a little bit about how the types of research we're doing in the US right now on integrating weather and climate information for renewable energy. And I'll be talking about work being done under the auspices of two of the primary agencies funding renewable energy research in the US. First, the National Science Foundation, and second, US Department of Energy. So I'll talk a little bit about NCAR, where I work, the atmospheric variability, and why understanding it is important to harvesting renewable energy. Talk about a project funded by the Department of Energy on coupling mesoscale to microscale models, and then finish up talking about climate information for renewable energy. So first, I work at the National Center for Atmospheric Research. NCAR is sponsored by the U.S. National Science Foundation. And I'm showing here a photo of the very famous building that is part of NCAR, designed by I.M. Pei, that sits at the Mesa in Boulder, Colorado. Now, I don't work at that building, at least not now. I did work at this building when I was a postdoctoral fellow, but we have a host of buildings across Boulder that all house atmospheric scientists and support folks and people doing research in lots of areas. We're known for our history of having large computers, computer models, high impact research results that translate into applications, as well as instrumentation that is used not only in the US, but throughout the world. Things like aircraft, satellites, lots of sensors, supercomputers, leadership in big data. And the NCAR is run by the UCAR, which is the University Consortium for Atmospheric Research, comprised of about 100 universities in the US and beyond. Now, within NCAR, I sit in the Research Applications Laboratory, and we do research in lots of fields, from aircraft icing, renewable energy, surface transportation, transport and dispersion of contaminants in cities, health, etc. And the mission of the Research Applications Laboratory is to conduct research and transfer technology to provide societal benefit directly. Okay, getting into why do we care about the atmosphere in harvesting renewable energy? You know, for those of you who are not meteorologists, maybe it is not quite so obvious. We have flow on global scales that is constantly changing, that we model with global scale models. Those models then feed into synoptic scale models, where we can see passing weather systems across continents. Those again then feed into wind plant scale models or solar plant scale models to enable modeling for renewable energy. Now, even within the plant scale models, we often see change in time, and we need to understand that non-stationarity in order to be able to harvest the flow. And then down into the turbine scale simulations that we do, where we calculate the vortices from the tips of the wind turbine blades and how they impact the blades behind it, so that we can estimate the amount of energy harvested by each row of wind turbines. And then from the finest scales, it feeds back into the larger scales, so that we end up with a spectrum of energy that one can see here, where here we're looking at energy along the y-axis and scales along the x-axis, where the largest scales is where we have most of the energy that feeds down into the scales at the wind plant and the turbine level. And you can see here that we know something about these scales by similarity theory, but modeling them and the energy transfer from one scale to another can really help us understand how to harvest that energy of the atmosphere more effectively. Now, I'd like to start by talking a little bit more about a project funded by U.S. Department of Energy. They have a program now called A2E, which stands for Atmosphere to Electrons. And part of that program is coupling the mesoscale to the microscale. First, what is this DOE A2E program? It's a multi-year U.S. research initiative that targets reductions in the cost of wind energy through improved understanding of the physics that govern the wind plants. So the goal is to ensure that as future wind plants are sited, built, and operated, we can harvest as much energy as possible through advances in the scientific understanding, so that we transform today's wind plant operating environment into the wind plants of the future, where we can optimize operation of the wind plants through things like controlling wakes, controlling pitch, yaw of the wind turbines themselves, and making it more effective to run these plants. There's a series of major research efforts, from plant performance and financial risk assessment through understanding the atmosphere into actually modeling the aerodynamics of the wind plants and the wind turbines themselves. We're going to focus here on the atmospheric science part of the research. Why do we need that atmospheric science piece? Many folks have said, why don't we just start with an inflow and look at what happens in the wind plant itself? Isn't that what we care about? But no, the atmosphere is this undulating, constantly changing organism that controls the energy in any particular region, is dynamically changing, and if we understand and can model those changes appropriately, we can harvest more energy. So without adequate representation at these wind plant scales, we could have mismanagement, using turbulence models incorrectly and not harvesting as much energy as we wish. Here I'm showing a picture of the lower parts of the tail of the energy spectrum, and this is stylized from a paper by John Wingard in 2004, talking about the terra incognita, where he explains why it is so difficult to bridge that scale between the large eddy simulations and the mesoscale simulations, where we have a difficulty difficulty understanding the flow in this range from about 100 meters to 1,000 meters that he calls the terra incognita. And to model this correctly, we need to get the appropriate boundary conditions, the appropriate numerics, physics parameterizations, including all the atmospheric effects such as radiative transfer, cloud parameterizations, heat transfer, etc., that are all important pieces of modeling correctly, as well as surface conditions and turbulence generation at the microscale. So without this mesoscale forcing for the microscale, we would not have the full characteristics of the flow. We would not get the non-stationary behavior or the transfer of energy across the scales, including information about turbulence intensity, how we model the wind turbine itself, and not getting a realistic simulation, including of the wakes, the tilts, the steerings, everything that goes into controlling the turbines in a wind plant appropriately. Now, ideally, we'd like to get the feedback into the atmospheric flow so that we can also model the downstream farms. And the work here is to improve the state of the art of modeling. So I have the honor of being principal investigator of a project comprised of 6 DOE laboratories listed here at the bottom, as well as NCAR, where we wish to build new high-performance computing-based multi-scale wind plant simulation tools that couple this full range of scales and includes the scale interactions that are needed to optimize wind plants to generate electricity. So the challenge here is that without that larger scale forcing, we cannot appropriately model at the micro scale either. So the approach here is grounded in verification and validation, beginning with case studies that really happen in the real world. We want to correctly model the microscale turbulence by having this forcing from the mesoscale and forcing through this terra incognita phase. So we start with 2 models, a mesoscale model and a microscale model. We also are grounded in data. We can use reanalyses that are historical models of past flow. We can also use measurements at specific facilities, in this case, both a flat case and a complex facility that I'll talk about in a few minutes. We choose the cases that we wish to run, and then there's 3 things that we really need to get correct. First, the surface and boundary conditions need to be consistent and connected between the mesoscale and the microscale. Second, we need to find a way to bridge this terra incognita between the mesoscale and microscale. And third, we need to initialize turbulence at the right scales in the microscale models so we get that turbulence flow between the different levels correct. We want to make sure that as we have non-stationary conditions, the microscale model will follow the changes that we see in the mesoscale models due to synoptic scale interactions. We start by analyzing our metrics, and we are going to care about the types of metrics that are important for wind plants. Are we getting shear correct? Are we getting wind speed at the level of the wind turbines themselves? Are we getting the turbulence intensity right? Are we seeing the energy spectrum appropriately? And the profiles of the wind at the different levels? If we do all of this correctly, we expect that we will end up with improved understanding and more realistic forcing, including non-stationarity and turbulence of these simulations through coupling the mesoscale to the microscale. So the first year that we were working on this, and we're now in our fourth year, we down selected which models we were using. At the mesoscale, we chose the Weather Research and Forecasting Model, WRF. This is a compressible low number model on a Cartesian grid with split time stepping, choices of advection schemes, and what's really important about this is allows nesting from the mesoscale into the large eddy simulation scale. So we can directly run large eddy simulations within WRF, and we can also get terrain characteristics as well as the physics parameterization so that we know the energy forcing through radiative transfer as well as advection in from the mesoscale. At the fine scale, DOE has gone with a model called NALU, which is an incompressible, finite control volume element based scheme. Second order temporal discretization, third order advection schemes, and that is what we wish to couple WRF to. NALU is currently being prepared for use in wind plants by adding all the facilities in the previous SOFA model built by NREL that is part of the OpenFOAM family of microscale solvers. Now, I did mention that we're going to ground this project in data, and we began the project looking at a flat terrain site in Texas, run by Sandia National Lab and Texas Tech University. It's a scaled wind farm facility where we were able to look at data representing very specific canonical conditions. The advantage there is that they have a 200-meter tower that has been operating for a period of years, and we can analyze the data from that tower and select cases that are appropriate for our study. So the first thing we did was look at a couple years worth of their data and developed windroses. And you see here, the windrose shows predominant wind direction from the south. And we also have plotted a breakdown of stability category. And I'm going to emphasize the blue bars on the histogram, where we see that the majority of the cases are under stable conditions. Okay, as it would be, it is very difficult to model stable conditions on using canonical conditions correctly. But as we'll find, we can simulate those stable conditions if we have the flow, the non-stationary flow from the neutral into the convective, back to the neutral, into the stable. A lot of prior studies have focused on near neutral conditions, but we find that at this site in Texas, which is quite representative of the high wind producing sites in the US, that there are seldom cases of near neutral, with it only being on the order of 7 to 8% of the time. However, convective conditions, as we find during the daytime, is also an important condition for harvesting wind as well. So first, we wanted to select cases. In this flat terrain case, looked at convective simulations and then also at stable conditions, which is dominant this site, but as I mentioned, very hard to model. We see that we can get the turbulence spectra pretty correct. You know, the red in this case, and I'll go back to this, is the measurements at that site. And we actually have 3 different models that we analyzed that all showed very close turbulence spectra. HyGrad, the SOFA model, and also the WRF LES, and those were all very close. And in the higher, the higher frequencies or the lower frequencies, larger wavelengths, very close agreement to measurements. But of course, as we always get, a drop off with model resolution in the very high frequency range. Now, this first year as we were looking at different models, we plotted profiles and found that the error between the models was much less than we saw variability in the measurements at the same time. So for the coupling, we're going to be looking at issues in the terra incognita, initializing turbulence, surface conditions, getting those correct, and then doing the large eddy simulations of the neutral atmospheric boundary layers, showing the importance of selecting the subgrid scale model, size aspect ratio, and order of the advection scheme. We did lots of runs. Our first paper on this is now available in Wind Energy Science. It's appearing now, where we did a variety of runs looking at sensitivity to these different advection schemes, etc. But generally finding that the differences between the three models that we analyzed were much smaller than in the choices of the advection scheme, the subgrid model, and those issues. So at that point, we decided that using the NALU model in the future will be adequate for representing the microscale turbulence. Okay, now we want to think about how to couple the mesoscale to the microscale effectively. And for instance, this diagram shows what happens on a diurnal cycle, where we are always going to have changes of velocity, temperature, heat and moisture flux with altitude and with time. So for instance, we see the light blue arrows show it on a diurnal cycle. The heat flux is going to change and then impact the temperature gradient at different times of the day. So we want to get that information from the mesoscale model to the microscale model. So we're going to be directly looking at the tendencies or the changes in time of these important variables and assimilating them into the microscale model. Here is an example of a particular case where we look at how the different terms do contribute to the tendency or the changes in the velocity. The top left, we see the U component of velocity, and that shows generally what U is. Now, the tendency or its rate of change is the top middle figure, and we see that it is actually rather important, ranging from about -16 to +16, maybe not quite that far in the shading meters per second. Only part of that comes from the pressure gradient term on the top right, which is what is typically used as the forcing. But we also have very important terms on this bottom that contribute. The advective term on the left, Coriolis, very important to the tendency in the middle, and then the PBL or the diffusive terms that generate, that look at the diffusion of the high energy modes is also quite important. These add together to form this tendency that alters the wind speed. That's what we are then adding to the equations of motion as seen in the red terms on the top right here. So one way to do this, we're going to model a diurnal cycle where we have changes in velocity with time on a rather clear canonical day, and we are going to include these tendency terms as well. We also simulated a strong frontal passage case where we see here that if we model with, using standard WRF large eddy simulations without any nesting, that we do not get agreement, and in fact we get a large drop in wind speed during that frontal passage. But if we nest the large eddy simulations, we start seeing the type of shear that is expected by using this nested large eddy simulation. So I'm going to show you a case modeled with a microscale model that includes the tendencies of the mesoscale model, representing this Swift site in Texas on November 8th, 2013. It was modeled at 10-meter resolution using 50 million mesh cells on 1,000 cores. And the idea is to internally force using the WRF. And I'm going to start the simulation, and originally we start at 6 a.m. local time, and you see very fine scale turbulence at the beginning during the stable conditions. As the sun comes up, the cells grow. We start getting a longitudinal rolls, and then I'm going to bring this backwards a little bit to where we see the longitudinal rolls develop. As heating increases, as we get closer to noon, those rolls turn into cellular structure, as we know happens in the atmosphere. We get very convective conditions, and we can see the convection growing in scale as we are in the middle part of the day. But then as the heating dies off, we go back through the rolls and into the fine scale turbulence again. So here we have successfully used the mesoscale to force a time varying diurnal cycle at the microscale using these methods. Okay, we've done lots of other studies related to this, looking at what about these terra incognita issues? Can we bridge that gap? What does it mean? How do we define terra incognita? At the beginning, I mentioned the scales from Wingard's paper, where the top end of the terra incognita was considered about 1,000 meters in that paper. But in some work that we did, especially by Raj Ray and Larry Berg of Pacific Northwest National Lab, we were able to confirm that it really is, the terra incognita scale goes to the top of the boundary layer. They did lots of different runs, analyzed them at different types of grid spacing, and here you can see the different grid spacings. And what happens in the terra incognita when you are not modeling it appropriately, you get these spurious rolls that are numerical in nature, not the physically induced rolls that we saw that happened during a diurnal cycle, but really numerical rolls. And this work really did confirm that the upper end of the terra incognita does reach to about the top of the boundary layer. And we found that we were able to make some general recommendations for how to model through this terra incognita. First, avoid using mesoscale domains using grid spacing smaller than the current height of the boundary layer. So if you have a boundary layer in a convective day reaching to 3.2 kilometers, you should not use 1,000 meter grid spacing for that domain, or you may get these spurious numerical rolls. Okay, found that it was fine to use either of two well-known boundary layer parameterizations, what are known as the MYNN or YSU schemes. Both of them work fine as long as you obey the rule on the spacing. And third, avoid driving microscale simulations with just a mesoscale simulation, especially from a reanalysis. It is really helpful to nest into the LES simulation in the same model, then to hand off to the microscale model. Otherwise, you end up losing a lot of the effects of the parameterizations that include radiative heating, clouds, lots of the things that are important to modeling at these scales. Now, I had also mentioned that it is important to be able to initialize turbulence at the fine scales. And the team has done a lot of work on that, and I'm going to highlight some work by Jeffrey Maroca of Lawrence Livermore National Lab, as well as Domingo Manos Esperanza of NCAR, a paper that he published recently in James, and looking at LES of a diurnal cycle from late morning through evening transition into nighttime. A particular case in November of 2013 at the Swiss site, and here I am showing specifically some work of Jeff Maroca, where during convective conditions, even without adding any stochastic cell perturbations, we found that even the fine scale we develop turbulence. And that's because the buoyancy terms are strong enough to develop that turbulence. However, during very stable conditions, we do not develop turbulence unless we add these stochastic cell perturbations. And these, in this case, were temperature perturbations. It takes a while to develop downstream, and it was important to get that during neutral and stable conditions. Okay, after we did these canonical flat terrain cases, we then began to leverage some results of the Wind Forecast Improvement 2 project. And this is a DOE-funded project in the Pacific Northwest of the US, where there is very complex terrain, great wind energy sites. You can see here wind turbines surrounding mountains. Mount Hood is predominant here. And in the bottom right, you can see a real photo of the type of terrain-induced waves that are typical in this area. So in complex terrain, you not only get these waves that make a difference for wind energy, you end up getting cold pools in the valley, you get wakes from the mountains, all these interesting behaviors that are difficult to model correctly. So what do we have to do here to model at the micro scale and capture that mesoscale flow correctly for those wind plants? We want to simulate the evolution and variability of the heat flux, wind speed and direction, potential temperature, turbulent kinetic energy profiles, all these phenomena that are important. And as I mentioned, topographic wakes, mountain waves are important, evolution of a diurnal cycle. We sometimes get easterly gap flow, because we have these gaps in the terrain. Frontal passages are important, as well as we get stagnation sometimes in the cold pools to the east. Now, one thing that we did at NCAR, led by Branko Kosovic and Pedro Jimenez, was to develop a new three-dimensional planetary boundary layer scheme that does not assume Mononubikov similarity, and it allows heterogeneity of the surface conditions. And this simulation shows the U component of the wind. As you can see the development of the topographic waves, you can see this mountain wake in the lee of Mount Hood. you can tell that the differences in wind speed that we see in these different regions are going to make a huge impact on harvesting wind energy at the sites in their lee. And we really do have wind farms in the lee. And we're going to be moving on to actually modeling the flow in those wind farms themselves, looking at the power generation and using that information to determine the details of this flow. But the type of situations you see here, you know, the mountain waves, the wake, all due to adding the new three-dimensional PBL scheme. I really like to look at this also in terms of vertical velocity, where I think you can even see the very fine scale structure in the waves, in the wake. You can see all the scales of the waves in this same simulation, all formed because of the complex topography. And we're getting better at modeling these situations as we've had opportunities to improve the parameterizations in our models. Okay, so we did lots of modeling. This is a particular November 12th case. It had an observed wake from Mount Hood, similar to the prior case that we just saw the movies of. We're trying to see whether it impacted the site. Okay, here on the left are the mesoscale models at two different resolutions, one at 3 kilometer, the middle plot is at 750 meters, and the right is the actual profiler. Here you see that the 3 kilometer solution showed a wind speed that was too high, and it was misleading, versus when we, because of the complex terrain, when we resolve the terrain flow and down to 750 meters, we get wind speeds that are much closer to those in the profile, the sounder from the profile as well. We also find that at 750 meters, the errors are much smaller. Therefore, in complex terrain, it is useful to use a much higher resolution, and it's an important thing to do at the mesoscale. Okay, we also looked at lots of other situations. I'm going to move on. It's complicated because it depends which direction you're measuring the wind flow from. In general, we get the general energy spectrum pretty correct. So now we're looking at deploying momentum perturbations in addition to the temperature perturbations at the micro scale within WRF. We're also looking at internal mesoscale terms added into, I just lost my presentation and went back to yours. Here it is. And see that at the micro scale, and building a library of pre-computed turbulent flows as a precursor. So in general, we did find we can do non-stationary cases. We can get the microscale model following the mesoscale model, does enhance the realizations of these simulations for wind plant optimization. Now I'd like to talk a little bit, move our scale of variability to more of a climatic and interannual variability scale, where this is a project that we did in collaboration with NREL a couple years ago. Where we looked at the interannual variability of the renewable resources and how that's likely to change under climate change conditions in the next 50 years. And will these resources increase, decrease, remain constant, or does it depend on the particular region, time of year, etc.? And what types of weather patterns are most important? So to do that, we looked at modeling, harvesting information from models both under current climate conditions as well as those future climate conditions. Current climate, we based on the climate four-dimensional data assimilation analysis. Now, an analysis uses real observations and basically interpolates in between them using a model. And in this case, the model was, it was the MM5 model, which is very similar to the WRF model that we were talking about at the mesoscale previously. For the future climate runs, we were using the NARCAP simulations, which are downscaled climate runs over the US, the North America reanalysis, climate change predictions. Okay, are we not seeing it all?
Yeah.
Okay. Our goal was to produce a database that can then feed into NREL's regional energy deployment system that includes interannual variability. And here's the years that are covered both by the CFDDA and the NARCAP that I just introduced. So the process here was first look at variability under current climate conditions using the reanalysis. We wish to get to a proxy future climate that also describes the variability over a certain length of time. We wanted to make sure, however, that we had realistic patterns that were comparable to two different time periods. So to do that, we thought we could not use the climate projections directly because they're known to not regenerate the same patterns even under current climate conditions. So we wanted to capture the patterns correctly. We used a technique called self-organizing maps that generates those patterns using neural networks. And we looked at a series of 3 combinations of NARCAP runs, combinations of global climate models and regional climate models. Under current climate, we compared their frequency with the reanalysis, chose the one that was closest, used that one for future climate, projected on the same SOMs from current climate, applied a transform for the trend seen in the temperature, and then did proxy selections using Monte Carlo selection techniques to generate this proxy future climate that had the correct frequencies. First, I'm showing here the mean wind speed and its interannual variability in terms of a standard deviation across years for wind speed at 80-meter hub height. And you see that the variability on the right is similar in pattern to the mean wind speed. We can do a similar calculation for solar power, looking at the mean over the US as well as its standard deviation showing interannual variability. And as one expects, higher resources toward the south, lower toward the north, variability again similar to what we see in terms of the mean. We can slice and dice this in all different types of way. To feed the NREL's READS model, they needed 366 regions broken down, as shown on these plots. We sliced and diced. Here you see the difference for the fall in terms of morning, afternoon, evening, and nighttime, different times of day, different seasons, etc. So slicing and dicing them that are most useful for NREL's model. Then we generated the self-organizing map model patterns by first taking means of the reanalysis and then its standard anomaly for each day of the year. Building the self-organizing map patterns, down selecting to 24 maps that cover the variability of the model runs. Under current climate conditions, we looked at 3 combinations of global climate model, regional climate model runs, and found that the one that agreed best under current climate conditions was the CRCM-CCSM pair. So that's the one we're going to use for the future climate analysis. We tested the combination. This shows the future wind speed anomaly patterns of each of these 3. And, as I mentioned, we are down selecting to CRCM CCSM. So for that one, we can look at changes in the seasonal pattern frequency, which gives us information on how the patterns change at different times of year that's useful for doing then the selection. So then we generated the proxy future climate by identifying for each day the SOM pattern, under current climate, and then using Monte Carlo selection to choose a day from the current climate for the future climate, applying correction statistics to agree with that frequency that was observed in the future, generating a proxy climate. So we can come up with these correction factors that again depend on time of day, season, and region of the country. What did we find? Okay, again, you can slice and dice this in many ways for wind speed. Here I'm showing changes across season in the US that we found. In the winter, we would expect a positive increase in wind speed across the northeastern United States and negative change across southern US. In the spring, it's mostly a negative change, so decrease in wind energy output during spring periods. Summer and fall, we get a variated pattern where especially in the fall, we see a decrease in the eastern part of the United States, increased places like Texas and California. This could be useful information to planning where to deploy wind energy. But also note that our scales only go from -10 to 10. So we're talking about roughly 10% change, but it's regionally variable and varies across the seasons of the year as well. Now, for solar radiation here, I'm showing you, we have plots, we have more plots than you want to see, but for the morning, different types of times of year, you can see that in the winter, we get less solar radiance in northern US, presumably due to enhanced cloud cover, but more solar radiation in the southern US. Versus in the summer, we see a slight increase across the entire US, with the exception of a few small features. So again, lots of ways to slice and dice this data. So in summary, predicted change is only about plus or minus 10%. But regionally, we can see up to about 20% for certain types of patterns. Regional changes we can predict to within about 10% of current values. And the small diurnal signal is evident, but the seasonal signal is predominant. So I didn't even choose to show the diurnal because it was much smaller than seasonal. So thank you for your time and attention. And at this point, I'm glad to take questions.
Yeah, thank you very much, Sue, for this excellent overview of the issues related to modeling, particularly wind power, but also solar towards the end. So we're taking questions now. As we said at the beginning, we have about 5-10 minutes. And we have received one, which I'm going to now say loudly, and but we please add other questions to this so we can assess them and answer them appropriately. So the first question we received is it possible to establish a network of wind stations where to get wind data that may assist in this project here in Malawi, Africa? If yes, how may our own governmental organization partner with you to assist in such a task?
Okay, so it seems like they're asking for wind observations. Now, the World Meteorological Organization cites wind stations all over the world, and anybody can get access to those data freely. And the Weather Organization in Malawi, I'm sure, has access to those WMO sites, as well as probably some very specialized sites that may be put up in the country, like in the US and in Europe and Australia. Many of these countries have lots of mesonets that are put up by the government in addition to those very specific WMO sites, but I do not know very much about how many additional sites there are in Malawi, and I apologize, but certainly could work with folks there to look for those sorts of things.
Okay, thank you, Sue. Another question is about, so far we seem to have heard about wind and solar. What work has been done on rainfall precipitation and river flow for hydropower? If you
actually quite a lot. People have, just as hydropower has been big for a lot longer than wind and solar, people have been modeling it and predicting hydrological flow for long periods of time. Again, I have knowledge more about the US, and some of you probably know about European models than I do. In the US, the NOAA recently deployed the National Hydrological Model. It actually is based on WRF, the same mesoscale model I've been talking about, and allows accurate prediction of precipitation, evaporation, through the physics packages in WRF, but then it also discretizes all the streams in the United States to 100-meter accuracy and details the flow from one segment into the other. When it rains, it models the flow from specific areas using appropriate terrain into the basins, and it's probably one of the more accurate water models to date. It's also being deployed in areas around Europe that I'm aware of, as well as many other areas. It really is the brainchild of David Gochis of NCAR. He works in the same part of the laboratory that I do, and it continues to advance over time, and we expect that similar things are being done elsewhere so that we can get more and more accurate models of hydropower as well.
Okay, thank you for the answer. I'm also checking if there are questions here from the audience in Norwich. No questions here. We're going to take another question from the audience online. So, are the mesoscale wind models being used only for the optimization of wind farms operation, or are they also being used to plan new wind farm projects? If not, why?
Yeah, no, thank you for that question, and I apologize if I misrepresented that. Yes, the mesoscale models also are being used to plan new wind farms. Particularly those wind farms in complex terrain. Many of the models like WASP have a limitation on the slope of the terrain, where WRF can model scale up to extremely high slopes, on the order of 40, 45 degrees, and you're able to see the patterns during predominant wind conditions. That's one reason that folks particularly use mesoscale models for planning sites. For instance, if you were planning a very complex terrain site, you might want to look at the windrows, see where the predominant wind speed and directions are, run the mesoscale model through those. Even at the mesoscale ranges, you can afford to run the mesoscale model through a year or two worth of real data and downscale it to see what the flow is going to be in the plant. And that way you're able to make even better estimates of where terrain is going to block flow, where it will enhance flow, where upstream turbines will perhaps impact downstream turbines, all these issues that are important for siting plants as well as controlling the turbines. So thanks for asking that question, because I didn't want to leave that misimpression that, of course, yes, it is smart to use mesoscale models for siting wind farms and doing the micro siting of the turbines within the wind farms as well.
Okay, thank you again for these questions. I may ask one final question myself, and then we just finish off with some reminders. So I'd just like to ask you whether you actually also assess the impact on the power generation through the modeling you do. So we've seen a lot of impacts and changes depending on whether you look at orography or graphic factors or not. How much is this affecting the actual power generation?
Okay, so obviously, wind speed is a first part of the calculation of power, but then you need power curves to translate that into real power. And for, every turbine has a cut-in speed, then a range where there's a cubic translation from wind speed to power, and then you end up at, rated power before it cuts off. So that is a complicated procedure then that depends on the type of wind turbine that is expected to be deployed there. And there are ways to do that, and I know Alberto, your team, does do that in various cases, and one can make that type of power estimate with particular assumptions about the types of turbines that will be deployed. It's an important part of it. The part that NCAR does that I didn't talk about here was wind power forecasting. And for forecasting, especially on shorter range scales, we begin with information about the turbines at a particular farm and then train artificial intelligence models to convert from wind speed to wind power, specifically for each turbine type at each site. And we find that the empirical conversion is more accurate than using the specific curve for a particular turbine. But again, you need to have data to be able to do that type of a conversion.
Okay, so excellent. I'd just like to thank again Sue for this very interesting, enlightening presentation. Also show what is happening at the cutting edge of research in US, and it's important to keep this link also between US research and European research. That's also one of the reasons why we were keen to have Sue here and link it with the activities of, in this case, Copernicus climate change, but it could be other activities as well. So just in concluding the session, I would just like to advertise a couple of events that are happening in this area. And one is the training course that is going to be held together with WMO, the Global Framework for Climate Services, and the Beijing Climate Change Center in China, and the World Energy Meteorology Council. So this is May 18th to May 20 in Shanghai, China. And will be followed by the International Conference Energy Meteorology. That's the 5th one. Again in Shanghai, same venue, between 22nd and 24th of May, and you find the information on the links provided on this page. As I said, the presentation will be loaded soon. If you can take a note of that. In terms of webinar series, so this is getting towards the end. As I said, the ESEM activity, which hosted this webinars, is now formally ended, but we're happy to continue with this webinar and another webinar also during April. A date is to be confirmed, but it's going to be on bias adjustment of climate variables for the energy sector. So this is research that has been done under the predominantly under the ESEM activity. Again, I'd like to remind you about the ESEM demonstrator, and the link is here. You can play with energy, climate data, and we are very keen to hear from you, have your feedback. So please use the tab on the right of the demonstrator. When you go there, you will see it, and we look forward to your feedback. And I just want to thank again also the input on this from the ESEM activity and the ESEM team, and also the World Energy Meteorology Council, which co-hosted this webinar. So thank you very much again, everybody here on the Norwich at the conference meeting room, and the people on the webinar, and we hope that you follow us on the next webinar and the future activities as well that will continue. Thank you for your attention. Bye now.